Yeah.
Okay.
Right. Well, Andy's ready. Okay, everybody. Thank you very much for coming along, and I hope you find this extremely rewarding. It's a great opportunity, but you only make anything of it if you participate. That means you fill up sheets of paper, drawing the diagrams, engaging with it, trying to be one step ahead at odd occasion. Quite difficult, but that's what you've got to do. It's a struggle to understand these questions, and you won't unless you are actually doing them yourselves. So we're working together. That's the idea. It's not that you're lounging back there watching it all happen and you feel better about it. You've got to engage, and I hope you're writing things down at a high speed, lots of scribble, lots of calculations, and see if you can kind of be a step ahead in getting the idea. Okay, thank you very much, Andy.
Thank you very much, Robin. Good evening, everybody. Welcome back to BPhO round one training. And if you've been for the last two, welcome back. If you're new, fantastic to see you. So I'm Dr. Andrew French from Winchester College, and we're going to be going through some round one problems. So hopefully you've got the link from various formats, but let's just check that where things are. So we have, let's make sure, if I put something in the chat, can everyone see it? Hopefully, let's give it a go. So this is my book, by the way, but here we are. Here's the page we want. So this is on my website called the Eclecticon, and we have the one question per page workbook from 2013 to 2021. So there's more BPhO questions that you would ever possibly want to do. And I will put that in the chat just in case you haven't got that link. There we go. And so we're going to be working through some of the 2021 questions, one of the more recent ones, and with a few interesting diversions. So today there might be a bit of a 007 theme. Okay, so we'll sort of throw that in. Okay, so here we go. So if I just come out of this, right, so here we are, 2021. So the first question we're going to do is this one. Can I just confirm from my moderators, is my screen looking nice and clear?
Yep.
Fantastic. Right. So again, if you're new, we're going to have a bit of interaction here. So get onto the chat system, and I'm going to ask a few sort of quick fire questions. So let's have a look at this. So dry steam at 100 degrees Celsius is passed into 0.250 kilograms of water at 0 degrees. Note water containing a calorimeter. All right. So whose thermal capacity is equivalent to 0.01 kilograms of water. And then when the temperature is 30 degrees, it is found that this amount of steam has condensed. So, and we're going to use this to calculate the specific latent heat of steam. Now, we've probably given away quite a lot of what this problem is about. So can you write down something that you might think is useful, perhaps an equation or an idea that's less than about 10 words? Put that into the chat now, and in about 30 seconds time, we'll see what comes up.
Specific heat capacity and thermal energy, energy conservation.
Wonderful. Right. Excellent. So some ideas. So we've got energy conservation. Right. We've got specific heat capacity. That kind of stuff. Now, okay, any equations for specific heat capacity?
E equals mc delta T.
Fantastic. And we always talk about changes. The change in energy, in thermal energy, we some sort of mass times the specific heat capacity times the change in temperature. So the specific heat capacity is the energy change per kilogram per degree or per Kelvin, because 1 Kelvin is equivalent to 1 degree Celsius. Right, excellent. So these are kind of the concepts. So first thing we're going to need to do is draw a diagram to try and unpack this statement. There's lots of stuff going on there. So, but we've got a goal, I think, which is pretty clear. Calculate the specific latent heat of steam. Now, that's not quite the same as the specific heat capacity. Anyone put in the chat what that might well be? What's a specific latent heat? Okay, so go on. Yeah.
Sorry, energy needed to boil water to steam, energy required to change the state, energy per kilogram.
Great. So the this would be, so this is the one we put in there, and so I'm highlighting now. That's to raise, either a liquid or a steam state of something, m kilograms of that something by delta T degrees. Whereas once we go from, we have to go a phase transition, liquid to gas, or gas to or liquid to solid. There is an energy change, all right, and that is called the latent heat. So in this case, we've got a condensation. So if we got, say, for example, gas to liquid, all right, we've got a change here, which is the mass of steam times the specific latent heat, which we're going to call L. All right. So there we go. I'm also going to label this. So we've got M steam. L is what we want to find out. Let's have M water, this one here. And there we go. So, and we're also, I think we're told, there we got the specific latent heat of ice, which interestingly you won't need. But I think we also have the specific latent heat, the heat capacity of liquid water, which is usually given in a formula sheet. And hopefully those who might know what this is, it's 4180 joules per kilogram per Kelvin. All right, so that's something we'd be given in a formula sheet. Right, so let's draw a little picture to find out what's going on, because I think the calorimeter here might be the thing that's going to be sort of throwing some of you. I think, what is one of those things? So let's have a look. We've got some sort of, I can imagine a sort of big glassware here. All right, so this is my steam is going to go into here. Here's my steam. So gaseous water. All right, and I reckon we've got some sort of thermocouple. So a multitude of wires of different metals that have a sort of different response to temperature. Here's my water in the bottom. And the idea is my thermocouple can measure the temperature very, very rapidly without really kind of interrupting what's going on. Here's my water here. Okay, so this is going to be, so 0.250. Let's just make sure we can see the question. There we go. Kilograms of water. I want to turn myself a little bit better. Okay, plus the calorimeter. Okay. And this has been interesting, is we're not going to ignore the calorimeter itself. We're going to have to heat that up as well as the water. And this is kind of what makes this question a BPhO question rather than just a sort of standard A-level one. All right. So we've got a mass balance here. All right. Okay. And this is my thermocouple, something I can measure temperature with. Now, there we go. That's the kind of schematic of what we've got. This is what we call a calorimeter. Now, okay. And the steam is at 100 degrees Celsius. All right. So there we go. Okay. So hopefully that's given a bit more sort of visual sort of understanding of what our problem is. We've got steam entering this calorimeter. We've got some water in it. It's a mass balance. And what we're going to look at is sort of how the mass balance changes. So what's going to be our energy balance itself? So we had energy conservation here. So that's just how we start these problems. I think we did something similar last week with sort of water flowing in a tube and then heating up, kind of immersion heater concept. This isn't really a dynamic situation like this. It's like a before and after. So what's our energy balance going to be? Let's write this in words. So the energy loss from the steam, because the steam has condensed. Right, where does that energy go? Well, it goes to the energy gain of the water and the calorimeter. Let's spell calorimeter properly. There we go. Hope that's all right. Otherwise, I'll sort of write it badly and then we can just sort of assume. It's like sort of like a jazz chord. All right. So in other words, we're going to assume no losses. Right, so this is going to be our energy balance, our conservation of energy. So, and it might be a good idea just to write this in words, what is happening here. Now we can turn it to maths. So we've got different parts to this. So what we have, we've got the steam condensing. So the steam condensing, that's going to release some energy. And that's going to give us, so the mass of the steam, now if we labeled this one, yes, we have MS there. So the mass of the steam times the specific latent heat of vaporization, which we're going to call the specific latent heat of steam. It's really the specific latent heat of vaporization because we've got a gas to the liquid. All right, so that's this thing here. All right, for water. So that's the energy we get from that. we're also going to have, plus the steam will cool as well, because we're told, all right, the temperature is 30 degrees Celsius, right? So the water is basically at 0 degrees. So it's initially, let's pop that in here, at 0 degrees, so pretty much just melted, all right, but no ice. And so we add the steam in, the temperature then rises of the sort of ensemble of liquid to 30 degrees C, okay? And we've found that in that process, we've got 0.0128 kilograms of steam, all right? So obviously there will be some steam inside, which will be still at 100 degrees, but the bit that's condensed will become water, which are thermocouple measures, all right? So what do we got? We've got the steam cooling. So we've got the specific latent heat, the specific heat capacity of water, okay, Cl. We've got the mass of the steam, because now it's in a water phase, and we're going to cool it. So just to be really clear what's happened here, we've condensed the steam. So that's now steam to water at 100 degrees Celsius. So it's not steam anymore. And then we are going to cool the steam by 70 degrees, actually, all right, because it goes to 30 degrees. All right, so now we've got water at 100 degrees Celsius to water at 30 degrees Celsius. Okay, so i.e. delta T is 70 degrees Celsius. Now I'm spending a bit of time writing this all out, okay, because the actual mass of these problems is not too difficult. It's how you sort of set it up and how you get your balance. So what's happening to that energy? Well, that's going to be the heating up of the water that's remaining, and in fact the calorimeter. So that's going to be the specific heat capacity of water. We've got the original mass of water, and we've also got the equivalent mass of the calorimeter. So it says the thermal capacity of the calorimeter is equivalent to 0.01 kilograms of water. So let's call that M, I think. I'll put that to red to be consistent. Let's call that big M. All right. So what do we got? So we're heating the mass of the water plus the mass equivalent to the calorimeter, and it gains by delta T water, which is 30 degrees. Okay. So that one there, that's going to be 30 degrees. It goes from 0 to that. So we've now got an equation. We're now in maths land. Let's just tell us what this means. So this is the gain of energy of water plus calorimeter. Okay. All right. So all we have to do is rearrange that. And it's a very simple rearrangement. We just divide everything. Well, we subtract this bit here from both sides, and then we're going to divide by the mass of the steam. So again, it's a really good idea to stay algebraic here, so you can see all the bits. Whereas once you've stuck in all the numbers, there's quite a lot of them, it'd be very easy to get confused, I think. So let's stay algebraic, shall we, until we get to a final point. So we're going to minus this one, and I'm going to divide by mass of steam. There we go. So there's our equation. Now let's put some numbers in. So the specific latent heat of vaporization of steam or water, so water going to steam, is going to be 4180. These are all SI units. 0.250, that's the mass of the water, plus the equivalent mass of water for the calorimeter. Then we're going to have delta TW is 30 degrees, because it started at 0 degrees Celsius. Next, I'm looking back to my diagram and checking that I've got the right symbols here. And I'm going to then 4180. So we could simplify that, but to be honest, there's no real need at this point. So the mass of the steam is 0.0128, and then the steam loses 70 degrees. There we go. And then we're going to divide that all by the mass of the steam, 0.0128, and that's going to be in joules per kilogram. Okay, so if we put that all into a calculator, and hopefully you will achieve 2.25 in standard form times 10 to the 6 joules per kilogram. It's quite a large number. All right, so this is very interesting, because of course this is why hurricanes work and typhoons. The condensation of water vapor into water releases a huge amount of energy, and that's what drives these sort of massive typhoons. I wonder if I can do this actually over the internet. I will just see. So we have a satellite receiver on the top of our roof in the school that I teach at, Winchester College. and I collect some data. Let's have a look at this one. Let's go for America, shall we? So I don't know, hope this will come across, but you should have a little animation now. So what we're seeing is an infrared, 10.7 microns infrared image from a geostationary satellite, and we get this via EU Metcast. So it gets beamed around the world, and we can stick a satellite dish and pick this up. Very, very cheap, actually. We need a satellite dish receiver. What you can see, maybe if I zoom in and find where the hurricanes are. There we go. So these are an impressive one, hitting California about a month ago. This is from a geostationary satellite. So it's basically staring at the Earth, sort of around where America is. And I think one of the really nasty hurricanes which struck the United States is about here. I think it might be this one. Oh, there we go. So there's a big one coming towards Miami. The eye is now formed. So this is sort of hundreds, if not thousands of kilometers wide. And they're powered by the latent heat of vaporization that you've just calculated. Okay, so let's go back to the problem. And there we go. So any questions in the chat about this or the style or what we've done? Anything I can sort of show the question in its full glory? Nope. Okay, so we're going to have a little departure this one. I said we have a James Bond theme. So if you like these kind of questions, if you want a few more, so I have this website where you can you can download all the BPhO stuff. So if we go there, this is the physics one. If we kind of go up to the sort of top level, let's go for this one here. So if I click on physics and I go to questions, so these are all kind of based on pre-university stuff, so A levels really. And if we look at the one that says specific heat and cooling, so the idea, I set quite a few of my students these questions, lots of notes here, and then you've got some questions. So if we go right to the bottom, there's a little question here about James Bond. So I'm going to go and do a little print screen of this, and we'll give a go at this one. So it's very similar to what we've just done. All right, so I'm going to go and put that aside. So you won't have this. So I'd like you to have a little read of the question. All right. Let's give you a minute or so to have a little read of that, and then we'll give it a go. Make that as big as possible. Okay, so James Bond asks for a martini, of course, shaken, not stirred. Now, a dry martini contains gin and vermouth in various proportions, is shaken with ice cubes, and is usually topped with an olive. So for simplicity, we're going to assume the following. So our cocktail liquid is 250 cubic centimeters. It's served at 5 degrees, and the average density, so we've got a mixture of alcohol and water, is 0.9 grams per cubic centimeter. And the specific heat capacity is 1200 joules per kilogram per Kelvin. All right, so we might have some ice as well as pure ethanol. Okay, so that's why it's the slightly higher, because remember, ice would be 4,200-ish, something like that. Okay, so what's happening? So James wears a 10-gram metal ring with this specific heat capacity, 370 joules per kilogram per Kelvin, from the Q department, which unfortunately malfunctions and immediately heats up to a temperature of 500 degrees Celsius. So, of course, James Bond, being super smooth, he removes the ring without even batting an eyelid, drops it into the martini. So, assuming no evaporation occurs, and we're going to ignore the calorimetric properties of the martini glass, okay, what's the final temperature of the martini? Okay, and the second question is, in order to lower the entire mixture to 007 degrees Celsius, of course, how much ice do we need to add? Assuming all the ice melts and no heat is transferred to the surroundings, the ring is removed first, of course. So let's go and do this. So what do we need? We need some diagrams. So firstly, let's do part one. Okay, so we've got our martini glass here. Okay, there we go. There's our super artistic drawing of a martini glass. And we're going to add our ring. Here's our sort of very, very hot ring, okay, which is sort of glowing hot. That is going to go into our martini glass. So T ring is 500 degrees Celsius. The mass of the ring is 10 grams. And our specific heat capacity of our ring is 370 joules per kilogram per Kelvin. All right, so initially, what's the temperature of our martini? Well, our initial temperature, we look in here, okay, it's 5 degrees. So let's just unpack our question. So T0, we'll call it that, is 5 degrees Celsius. What else do we know? Well, the volume of our martini is V is 250 cubic centimeters. The density of our martini is 0.9 grams per cubic centimeter. And the specific heat capacity is going to be 1200 joules per kilogram per Kelvin. All right, so what happens? So that's the sort of before situation. So these kind of problems are like momentum and collisions. In fact, the first problem we did in this course. And so you want to kind of before and after. It's not a dynamics problem like a sort of something with kinematics, or you'd apply Newton's second law or something like that. So after the ice is put into the martini, it does its thing, it transfers energy, and we get a kind of equilibrium. So what does that equilibrium look like? Well, the ring is at the bottom of the glass. There we go. And we've got a temperature T. Okay, and this is what we're going to try and find. So that's going to be T there. All right, assuming no evaporation, okay, which is probably an enormous assumption, but because it is 500 degrees Celsius. But hey ho, you know, this is James Bond. We can be a bit playful with our physics. Right. So what's our energy balance? Let's write down something very similar to we had before. So what's our energy balance going to be now? Okay. So if we have no loss, so what's going to be what would we say for the ring? Put something in the chat. Put something in the chat. If you can give me an equation, that'd be even better, because I've defined everything now. What's the energy we get from the ring? What have we got? Are we still there?
Mass times specific heat capacity times change in temperature.
Brilliant. So using the symbols we've got, so CR, which is what we've defined. So another massive tip is that if you go on to the effort of setting symbols to everything, use them, because C might correspond to different things. So we've been pretty precise here. So CR is the specific heat capacity of the ring, and C is the specific heat capacity of the sort of ethanol water mixture, the cocktail. All right, so CR times M, okay, times our delta T. What do we got? We've got TR minus what we want, which is the final temperature. So that's the temperature change. Okay, so what's that going to equal? We need to do the same for our ring and also for our liquid. So what do we got? So we can have so C times the mass of our liquid, which is the density times the volume, times the temperature. So there we are, times the temperature change. So T minus T naught. That's going to be the heating of the martini. Okay, there we go. So there we are. There's our energy balance. So now we're in maths land. So what do we want to find? We want to find T, but it appears on both sides of the equation. So what we need to do, let's go and multiply it out and then sort of reconcile our terms. So we're now in math land. Okay, so we can put our maths hat on. Let's do this. So we've got CRMTR minus CRMT equals C rho V T minus C rho V T naught. Let's put the T's on one side. So we've got T here. And I'm going to put a bracket and say, what have I got? So if we have, actually, let's do this side. So put the T's this side. So we've got T, we've got C rho V, and we've got plus CRM, and then put everything else on the other side. So we've got CRMTR, and then we've got plus C rho VT naught. Okay, let's just divide everything by what is the multiplication of T, and then rearrange the other side. So therefore, T is going to be CRMTR plus C rho FT0 divided by the bit in the brackets. So C rho V plus CRM. Right, yes, good. So there we go. We've got an equation. Now let's put in some numbers and we'll see what we get. So what's that going to be? So CR is 370. And we don't need to worry about, if you think about it, putting into kilograms, because we've got the masses on all sides. In fact, we could divide by a mass if we want. So by that definition, we can just sort of, as long as we've got grams on the top and grams on the bottom, all is good. So we can just literally use the numbers we've got. So times 0.01. So there we go. That is, actually, no, I have converted it. I apologize. I have converted it, I think. So 0.01 times 500. Okay, plus we've got 1200. Okay, times 0.9 times 10 to the minus 3. So remember, it's what have we got? We've got 900. Yes, so 0.9 grams per cubic centimeter. So I'm going to convert that. So I probably don't need to, but hey, let's do it. So divided by 1,000 times 250, and then times by 5. All right, because that's what T naught is. We're going to put that into C rho V. So 1,200 times the density, 0.9 times 10 to the minus 3, times 250. And then lastly, we've got the CRM, which is 370 times 0.01. So yes, I have converted everything into those. All right. So, and I guess what you could work out is that 1 gram per cubic centimeter. All right. What's that in terms of kilograms per meter? Do I need to do this? Yes. Well, I've got kilograms here, so I ought to do that conversion. So that's going to be, so 1 gram is 10 to the minus 3 kilograms, and 1 centimeter. Let's just check we have converted that. Actually, yes. So we'll do it per cubic centimeter. So I needed to convert just that into kilograms. That's all right. So that's where the 10 to the minus 3 comes in, because I'm converting the grams to kilograms because I've got joules per kilogram per Kelvin, but I don't need to convert the cubic centimeters because I've got a volume on the top and the bottom. All right. So if we put those numbers in, what do we got? If you've done this question, you'll find it's about 11.7 degrees Celsius. Okay, so that's part 1. So now what happens, we're going to add some ice, and we're going to turn this mixture into 007 degrees. So let's just draw a little picture of what's going to happen next. So there we go. Here's our martini. All right, so we take the ring out. The ring is now removed. It's only 11 degrees now. It's quite acceptable to remove our ring. And that's 11.7 degrees Celsius. And what happens? Well, we put some ice in. Here we go. And the ice melts. So we've got, this is our ice. There we go. Let's call that M kilograms of ice. All right. And then we've got this, which is T equals a chilly 007 degrees Celsius. All right. So what's going to happen now? Well, we need to do another energy balance. So what we're going to do, so we're going to cool the martini. And the cooling of the martini will be the energy to melt the ice plus the energy to raise the ice to the final temperature. All right, so we can assume the ice is at 0 degrees Celsius. All right, so let's do that. So what do we got? We've got the cooling of the martini. Probably let's have a cooling being in blue. Okay, what's that going to be? Well, it's going to be the specific heat capacity of the liquid, C, times the density, times the volume. So that's the specific heat capacity times the mass. And then what have we got? I'm going to call this, I think we'll call that T1. And we'll call that T2, just to be sort of, distinguish it from the T we had before. All right, so what have we got? Actually, we ought to, because we had T was 11.7, didn't we? So why don't we call that T? There we go. And we'll call that, I don't know, T star, something like that. So T minus T star. So that's going to be our CM delta T. That's the cooling of the martini. Now, what's that going to equal? Well, that must equal the energy. So we get the energy from the martini to melt the ice. So ML. So L is our, that's our specific latent heat of fusion of ice, which I think I give you. Do I give you this one? Yes. So there we go. Do I give you this one? Maybe not actually. So I think this is one I would give in the actual questions itself. So I'll give you that, which is, so this one. Yes. So that should be. Yes, it's 335. Okay, I don't think I've given you this in the problem. Apologies. No. Right. Okay. So for ice, L is 335, and that is going to be kilojoules. So that'd be times 10 to the 3 joules per kilogram. So that's the specific latent heat or fusion of ice. So liquid water to ice, right? To make that phase transition happen, this is the amount of energy per kilogram we change. That would have to be given. It is given in this sort of problem sheet, but not in this particular question. So there we are. I think we've got everything now. So ml, that is going to be the energy to melt m kilograms of ice. So that's energy to melt m kilograms of ice. And then what we're going to do, we're going to add that to the energy to raise my m kilograms of now liquid water up to T star from 0. Okay, so the thing on the right is all about the ice, and the thing on the left is about the martini. Okay, so we're sort of separating that and assuming the energy balance. This is the martini, and this is going to be all about the ice, which then becomes water. All right, so we need to raise the water all the way up to temperature T star. So C, and now this is water, so CW, not the sort of liquid anymore. It's a different one. T star, and we need M here. Okay, and C water is what we had before. So that's going to be 41. I think I said that's, what did I give you? Was that 8086? I think it was 80 in the previous one. Or maybe that will give you something slightly different. So let's use this one. So joules per kilogram per Kelvin. All right, so what do we need to do? So it's the mass of the ice we need. So, and now we're in maths land. We factorize out the m, and then we can figure it out. So therefore, if we sort of put this in a bracket, so we've got L plus CW T star equals C rho V T minus T star. Okay, and then we just divide by this one. So therefore, M is C rho V T minus T star divided by L plus CWT star. Okay, so this formula here, that'd be really hard to write that down just from scratch. You've got to start with your energy balance and then do some maths. So let's put the numbers in, shall we? So what do we got? We got so 1200 is C. Rho is 0.9 divided by 1,000. So that's kilograms per cubic centimeter. What have I just done here? There we are, it's back. So we multiply that by our volume, 250, and then 11.7 minus 7. Okay, and then we're going to divide that by our specific latent heat of fusion, which I'm going to give you as, what do we say, what it was, 300 and, where did I put it? There we are, it's up here. 335 times 10 to the 3, this one. So let's go put that in. So 335 times 10 to the 3 plus CWT star. So that's the specific latent heat of water, 4186. And we're going to multiply that by 7. So that's going to be in kilograms. And if we put that together, that gives you 3.48 10 to the minus 3 kilograms, which is about 3.48 grams. Actually, maybe it's a slight, I've used a 6 there. I might have to double check the final figures of that. That's the one I did before. So 4186, I think, is a bit more accurate than the other one. We're at that. So we're at 4180 is what I given the previous question. So it's something like 3.5 grams. Let's do that. And the two significant figures were correct. So there we go. About 3.5 kilograms. So, excuse me, 3.5 grams of ice. You add that to your martini, 11.7 degrees. You get it to 007 degrees Celsius. There we go. So 2 questions about energy balances and using things like CM delta T and ML. But the sort of, so in terms of the sort of algebraic ingredients, it's quite simple. But what makes these problems more complicated is the kind of balance that we are doing. So always start with the energy balance, write down what the left and the right is. So the cooling of the ring, heating of the martini. Previous question, what do we have? We had the condensation of the steam and the cooling of the water is the energy gain of the the cooling of the steam is the energy gain of the water and the calorimeter. So, there's a sort of energy exchange. That's the trick for doing these questions. All right. Okay. Any questions before we move and do something totally different? Okay. A positive silence, I hope. Right. Okay. So we're going to do a little bit of, actually, we'll do a very simple problem, I think. This would be quite a nice one. Another sort of water block thing. I think this probably might be ignored. And then we'll do an optics problem. So we're going to do N, then M, two different in a different order. Okay. So let's see if we can find that one. Let's find M. There we go. Right. So, because I think this is a very simple question, but I think it's one of those ones which you might not be sure kind of how to approach this. So what do we got? So in fact, let's just have a quick look. Aluminium block is attached to a Newton meter that records a certain weight of 6.6 newtons. And this whole thing sits on a mass balance and records a mass. Right, let's draw it. And then I'll ask a question about what else do we need to know here? What's this question all about? So let's just draw a picture. So here we go. We've got our beaker of water. There we go. And it's sitting on a mass balance. And that mass balance, there's going to be some springs involved, something like that. And that says 600 grams. That's our mass balance. All right. Okay. So what happens is that we then, same thing as here, and we lower this block. All right. And I think it's what might make this a bit confusing. It's attached to a Newton meter. That's usually something on a spring, isn't it? So we can think about sort of some sort of spring, a really sort of light one. Here's our spring here. All right. And then we've got our block of aluminium. Okay. So this is our aluminium block. Al block. And so we can think of our spring having tension T in it. So we've got a force T here. So T would be the tension, which is going to be our 6.6 newtons initially. All right. Okay, so that's going to be our initial one. Just check I've got that right. Yeah, that's what we're going to call T. Right, but that's now lowered into the water. So here we are. That's in the water there. Now, so what other forces are acting on our block, given it's going to be in equilibrium now? If you can put those into the chat for me, that'd be brilliant. What other forces are acting on the block?
Buoyancy.
Brilliant. Right, and that's the missing one. So I'm going to call this buoyancy or up thrust. Okay, so U is going to be the up thrust. And what else is going to be acting on the block?
Weight.
Good. There we go. This is the weight. All right, so W. There we go. So this is a force problem. All right, this is an equilibrium. This is a statics problem. Okay, it's going to be involving Newton's laws, that kind of thing. So we also need to have, gravity here. I think what we've got, that's 9.81 newtons per kilogram. Okay, so we pretty much defined our problem now. Now, what do we want? We want the new reading on the Newton meter. So that was originally T. So we call that like T naught. What is it next? We can work out what we want to find out what T is. And we also want to find out what the mass balance is. Right, so let's do the first bit. So the first bit, well, if we think about sort of equilibrium, in equilibrium, then T plus U must equal W. All right, now what is the up thrust? What's Archimedes' principle? If you pop that in the chat for me, that'd be great. Okay, let's while I'm doing that, it's 5 centimeters cubed is our block.
Yeah, people are saying force equal to the weight of the displaced water.
Brilliant. Yes, so the weight of the displaced water. So U is going to be the density of the
We do seem to have frozen there, but maybe Andy will come back in a moment. This might be the point, Anson, where you could give him a ring to tell him he's
That's exactly what I'm doing.
lost us.
Stand by. Whilst we're waiting, could I suggest people sort of think about how you might prove Archimedes' principle? So why is Archimedes' principle true? What's the statement? The statement is that the upthrust is equal to the weight of fluid displaced. Why is that true?
It is not possible to connect. He'll be back in about a minute. We're just resetting his network connection.
Okay, I think I'm back. Sorry about that. Not sure what happened there.
Yes, you are back. I can hear you.
Hooray! Right, it's good. Hopefully you haven't gone away. Excellent. Thank you for bearing with me, everybody. So I think we've only lost about a minute and a half, something like this. So hopefully I'm still showing my screen. Can someone confirm that you can now see some blocks of aluminium and that kind of thing?
We can.
Yep. Yes,
Wonderful.
blocks of aluminium.
So let's just have a recap now. So what we did, the first part, we lowered our block of aluminium in the water and we calculated the upthrust, and we've already got the weight, which is 6.6 newtons. So if the tension plus the upthrust equates to the weight, because we've got equilibrium, and let's put a little box around that, then we can use that to work out the new tension when we lower our block. And it kind of makes sense that the tension would go down because we've now got this extra force pushing it up. All right. So, you know, if you go and put on a life jacket and jump in the river, it's sort of, you've got a force on you. Right. So what is the mass balance reading? Well, this is by Newton 3. Okay. So Newton's third law. So every force we in contact, we get an equal and opposite reaction. So the force of the water by the block, so the force on the water by the block, well, that's going to equal U, all right, because that's the upthrust is the force of the water on the block, right? So it's an equal and opposites thing. So the reaction force at the mass balance, so therefore the force on the mass balance must equal what we had before. So it's going to be the weight of the water plus our upthrust. Okay. And what do we do? Well, initially the reading said 600 grams. So if we divided that, so the mass equivalent, all right, so we don't measure weight, we measure mass on a mass balance. So we need to divide that by G. So the mass equivalent is going to be 600 plus U divided by the mass of the water, by G, okay, the strength of gravity. So let's put that in. So what do we got? And also we need to multiply that by 1,000, all right, because U over G would be in kilograms, okay, because we've got U is in newtons. So that's going to be 600 grams. I won't use G here because I've got G for gravity. So 600 plus 2.45 newtons, okay, divided by 9.81, multiplied by 1,000. And if you work that out, that gives you 850 grams. Okay, so quite an interesting problem. We lower our block, the tension goes down, but the mass balance goes up, which you kind of would expect because we've got more stuff in the water there. All right, so a quick but nice question, but I think it's really quite illuminating in terms of ideas of equilibrium, upthrust, reaction forces, all that kind of stuff. Right, so we're kind of coming to the end, I think, now. So we normally sort of finish at about 8 to 8:45. So I think probably I will leave O to next time, which is a paradigm question, I would call it, and possibly the optics one as well, which is M. So these might be really good ones to have a go at next time. So M, thinking about Snell's law and refraction, that kind of stuff. It's a fairly straightforward question, actually. I think the one on O is probably not, and this is all about bending and materials. So this is a really nice one. So we'll probably start with that next time, and that will be really, really good to have a look at. But I think I'll give you a hint before we go. Let me bring my hints up. So this is probably, I'm going to draw the diagram for you. So if you want to have a go at just drawing this diagram, and then you can have maybe go at the question as a result. So what we can think about is a beam here. And I think we'll call the bar of side A 2 centimeters. And we'll go for B being this. So we've got a kind of cuboidal bar here like this. And this is a materials question. As you want to be engineers, this is all what it's all about. So here's my bar. All right. And to a certain extent, most things are kind of elastic on certain limits. So what we've got, this is going to be B, this length here. And we'll call this length B plus a little bit. We'll call that B plus delta B. And this will be A over 2, of course, all right, because it's symmetrical. And this bit here, this will be called the neutral line. Now, what does that mean? So this is where there's no compression or tension, all right? So we're going to assume, if it's bent a little bit, that bit there is B. So it's not bent, it's not compressed, it's not under tension, nothing like that. So no compression or tension. Now, if it's sort of bent in a circle, we can kind of keep going. Imagine sort of extending that all the way down. All right, we're going to run out of paper. There we go. And we'll call that angle theta. We'll call that radius from here, from the neutral line downwards. I'm going to call that r. Now, my question for you, using ideas of Young's modulus, stress and strain. So if you're not in the sort of sixth form, these concepts might be quite new to you. We'll talk all about those from first principles next week. But using ideas of stress and strain in Young's modulus, think about how delta B over B varies with radius and A. And we're going to prove this relationship. Okay, so that's something to see if you can do geometrically. And then we're going to combine that with Young's modulus, which is the stress over the strain. And the strain, well, I'll have to think about what that might be. Okay, so I think I'm going to leave that with you. All right, I think that will be enough to get started for this particular question. Once you know what this is about, this question sort of unlocks a world of bending things and analysing sort of elastic mechanics, if you like, which is pretty much quite a lot of civil engineering. So there we go. I'll leave that with you. Come back next time, and we'll start with this, and I'll probably finish off this paper. Actually, that would be great. And again, come armed with any questions that you've got on the previous. So just before we leave, is there anything in the chat that you'd like me to address?
No, seems all right.
Brilliant. Right. Well, thank you very much indeed for coming to do some physics on a Thursday evening. Excellent to see you. And I look forward to seeing you all at the same time next week. Am I back now? I get to actually plug the book. Someone's asked for it. So if I share the screen, there we go. I think this is acceptable. So if you go onto the eclecticon, here we go, and you go to, let's go to the main page. Under physics, there's a link to science by simulation. So if you like the sort of style of how these work, volume 1 is in print, and there's little summaries of all the different chapters. So there's all sorts of stuff from epidemiology to atmospheres to rainbows, fractals, radar, bit on money, politics, all sorts of stuff, and some important numerical methods of things as well. Book 2 is going to be in the works at the moment. It's nearly finished, and that's going to be models of classical physics. So pretty much all the stuff that you really ought to encounter before you embark on a university physics course or an engineering course. So things like mechanics, thermodynamics, ray optics, electromagnetism, plus some really nice maths, something called the calculus of variations, which is just magic. And then volume 3, which is nearly in the works, that will be things like special relativity, quantum mechanics, and some cosmology. So that will hopefully be about a year or so away. But volume 2, I'm very close to finishing. So maybe that will be in print in 6 months or so. There we go. You can access all the details. So the first book, this is available. You click on the link, and there's plenty of sort of videos. You can see the code. You can download all the code for each bit. And there's a little sort of visual summary of each one. There we go. I'll leave that. Oops. There we go. You can take a screenshot. Any more questions?